A mentor at a game-making competition once said to me, "It doesn't matter how, always add shadows to your game. It will always add a sense of presence and depth." In our case, we will simply take an existing texture atlas and make a dark cutout variant of it. To achieve this in code, we'll create a new component called Sprite2D Shadow. The shadow sprite will simply draw behind a designated target sprite, though offset by a specified X and Y amount. This offset is performed by getting the target sprite's transform and applying a simple translate operation on it before handing it to the shadow as its transform. In testing, this works pretty well for sibling sprites, that is, where the sprite and its shadow share the same entity. However, this breaks down very quickly if the sprites are simply cousins. To achieve proper shadow offset behavior regardless of familiarity, we need a way for one sprite to completely invert its inherited transform and override it with its target. In other words, we need to find a transform's inverse. Towards this end, we'll be using a process known as Gauss-Jordan elimination. In essence, this algorithm first constructs a matrix with twice as many columns. The first half is the original or input matrix, while the second half is an identity matrix. We then perform elementary row operations on this augmented matrix until the left side becomes the identity matrix. Once we succeed in this, the second half automatically becomes our inverse. Of the elementary row operations, there are three: the swap or exchange two rows, the scale or multiply a row by a non-zero value, and the add scale, that is, to add a multiple of one row to another. Next, we need a way to calculate a sprite's world transform. This is done by multiplying its own or local transform by its parent, then by its grandparent, and so on, until we run out of ancestors. Another name for this is the local to world transform, as it can be used to transform any local position that is relative to the entity itself to a world position relative to the world's origin or zero position. With the transform inverse function, the world transform getter, and using some basic rules of matrix mathematics, we can now calculate the final transform for our shadow sprites. With this budding new matrix library, our little game engine is getting quite powerful for its size. We now move on to the next big requirement: multiple draw layers. But first, some background. Up until now, we've simply been drawing our components in the order we find them in the scene tree. As has quickly become apparent, this does not work very well for our shadows. Instead, we would like to have better control over what components draw before what others. To achieve this, we allow each component to specify a layer number. We then sort the components into buckets, each with a matching number. These buckets are often referred to as draw queues or layers. And finally, we update our Game2D class. Instead of just drawing components as it finds them in the scene tree, it will now add them to our new Draw Layer list.